Hi, in this video, we're going to go over the logistic function and S-shaped curves. Okay, so what the logistic function does for us in standard logistic regression is that it gives us a way to convert any number along the number line from negative infinity to positive infinity to the interval of 0 to 1 for probabilities. So we can take any number, and with the logistic regression curve, we can convert that to a probability between 0 and 1. And so this is a critical step in being able to fit our models. Now, we're going to go over a couple different possible S-shaped curves. The one that is by far used the most is what we'll call logistic curve. But there's also probit, quotient for Cauchy, and probit uses normal distribution. And we'll also talk about one that's used in survival analysis. If you don't know which one of those to use the logistic curve. And let's go ahead and get into it. All right, so big idea here is that we're going to use a mathematical function to convert real numbers to something on the 0-1 interval. All right, so here, this is the logistic function. And so here I have f of x, or f of z, is equal to 1 over 1 plus e to the negative z. All right, so this e is the natural logarithm base. This is infinitely long, like pi. It's approximately 2.71828. So it's infinitely long decimal representation of it. And if you look at this, you'll notice that I've got 1 here, I've got 1 down here, plus something here. Now, if you remember from college algebra, a positive number to an exponent is always going to be a positive number, regardless of what the exponent is. And so this item here is always going to be positive. It could be super small, close to 0. It'll still be positive. It'll still be there. It'll be greater than 0, or it can be super big. All right, so if this is close to 0, if it's very small, then this is just a little bit more than 1. All right, so if I divide 1 by something a little bit more than 1, I'm going to get something, that's just a little bit below 0, or sorry, a little bit less than 1, but close to 1. Now, think about the other direction. Let's say this is a huge number. I plug in like negative 1 million in for z. Then this e, that'd be e to the power of 1 million, will be a super big number. 1 divided by a super big number is going to be very, very small. This will be close to 0. And so just conceptually right now, you can see that this function is going to keep everything between 0 and 1. If this z value is very, very large and negative, then it's going to be close to 0. If it's very, very, very large and positive, the function is going to be close to 1. Now, we have 2 major representations. We have it like here, where we only have e once, but a lot of times we don't like that negative sign. The negative sign, a lot of us mess things up when we're doing our college algebra calculations. And so if I multiply the top and bottom by e to the power of z, which is equivalent to multiplying by 1, I can see that I get this presentation, and now I don't have a negative sign floating around. This presentation, I don't have a negative sign, but I have the e twice. Here I have the e once, but there's a negative sign in here. Whichever way you prefer, both are right. Use the one that's easiest at any given moment. All right, so let's go ahead and just take a look at what does this curve look like when I graph it. So I'm going to use ggplots, and you'll notice it's a little bit smaller so I can get the entire curve on here. All right, so it's very flat to the far left, and this is really close to 0. It's very flat to the far right. It's very close to 1. Now, it doesn't actually equal 0. It's just really, really close. It's a little bit above 0. And here, it doesn't actually reach 1. It's just really, really close. It's a little bit below 1. And then we have this smooth curve coming up. All right, well, if you've taken calculus, you'll notice, hey, that looks like a differentiable curve. And it is. Use quotient rule and the exponential rule, and you'll see that it is in fact a differentiable function. Very nice. And so, this is, looking good. And you'll notice that here, this is, we've got, concave up, inflection point, concave down. And so you'll notice that the limit as we go to the left is going to be actually 0, but it'll never actually reach 0. The limit as it goes to the right is going to be 1. It'll never actually reach 1. It's bounded above. It's a continuous function. So it's a bounded function, strictly increasing continuous function. That means it has a lot of nice mathematical properties right out the gate for us. If you've taken mathematical analysis, like this has like a lot of nice features to it. All right, so as z goes to negative infinity, that curve goes to 0. It's always greater than 0, but still gets close to it. And as z goes to positive infinity, f is going to approach 1. All right, so I flipped these. This should go with that. But all right, so here, as z approaches negative infinity, f goes to 0. As z goes to positive infinity, f goes to 1. Okay, now when I plug in exactly 0, then the curve is exactly equal to 1. Anything to the power of 0 is 1, so I have 1 divided by 1 plus 1, which is 2 on the bottom. All right, so this is important for us. So now let's go ahead and take a look at the derivative of the logistic function. All right, well, if I take the derivative, you'll see that, and here I use quotient rule for this. I've got something positive up top. I've got something positive on the bottom. So it's a ratio of positive numbers, which is in fact, again, a positive number. So I can see that the function is always increasing. All right. And we'll notice that there are no minimums and there are no maximum values to the curve. So the function is strictly increasing and bounded above and below. And because it never reaches 0 or 1. If I take the second derivative, all right, so I'm taking the derivative of the derivative, and you'll notice that I can get 0 in the numerator if I plug in 0 for z, okay? And then I have something that has to be positive, and this has to be positive, therefore the whole bottom has to be positive. And so now the thing that determines its sign is where is the sign of this. Everything else is positive. This determines if the second derivative is positive or negative. All right, so if we're to the left-hand side of the number line, we're going to see that we're going to get a number less than 1, which will make this. Sorry, if it's to the left of the. Oh yeah. So we can see that it will be concave up to the left, and it'll be concave down to the right. And if I plug in 0, I get exactly 0 here. So we know that we have an inflection point there. All right, so how do we connect this to statistics? Well, what we're going to do is we're going to use this equation here. Now, how the heck did I get to this? All right, well, what we're going to do is I'm going to take these values here. So just like in linear regression, I'm going to take coefficients and predictor variables. So here's my intercept, coefficient, predictor, coefficient, predictor, and so on. And I'm going to put this in for z right here, like that, just like I had before. So here, I can put it in this format where we have the 2 z's, or I can put it here where we have the 1 z's, but it's negative. If I go through and do my college algebra and solve for the z part of it, I solve for all of this junk going on here, we'll see that this is going to be the log odds of that of the event. All right, well, so now we have a direct connection. This is nice. So we have here I have my what looks like linear regression coefficients and predictors, and it's going to be equal to the log of the odds of the event. That's a nice connection. That's very easy. So that means that this logistic curve gives us a lot of features. It has a lot of mathematical features just right out the gate from a calculus and analysis point of view, but also I have a connection from odds that's very easy to work with. All right. So here, P is the probability of the binary outcome. And, log is natural logarithm. The betas are our model coefficients, including the intercept, and the X is our intercept variables. All right, so let's make this a little bit easier. There's a lot of stuff going on here. So let's go ahead and just look at simple logistic regression. So here I'm going to have just one predictor variable and one coefficient along with the intercept. Now, something that I need to point out is that, remember when I did linear regression back in the day? There was always a little epsilon term floating around over here being added on to that combination of coefficients and predictor variables. Well, when we're doing regular regression, we're trying to get a distribution of actual observed values. When we're doing logistic regression, we're not really worried about individual values. We're looking at the average overall is what we're trying to get at. So it's a little bit coarser. It isn't as zoomed in as regular regression, but it's nice that we're not having to fuss with that whole epsilon term. So and this also accounts for random variability and deviations from our model, is that we're trying to fit the expected value, not the actual true observed value. All right, and so when I do this, this is going to take the place of the Z that I had before, so we can see in this presentation, or with the negative sign, so I multiply everything by a negative. All right, so now, when the slope is greater than 0, the curve is strictly increasing. The probability increases as X increases. If beta 1 is less than 0, the curve is strictly decreasing, and the probability of the event decreases as X increases. If beta 1 is large in magnitude in absolute value, then the slope at the inflection point will be very steep. There will be rapid change when the predictor variable value gets close to the inflection point. Remember that how steep it will be. And then if beta 1 is very small, then the inflection point will be very gentle, and we'll have slower change when we're close to the inflection point. Now, the slope will always be steepest near that inflection point. And that'll be where the curve gives us a probability of 1/2. Very large slopes will result in curves that are nearly a stair step. Very small curves or very small slopes will give us curves that look nearly flat when I graph it. It'll take a large increase in X to get a significant increase in the probability. All right, so let's take a look at what the impact of the slope has on the curve. So all these have intercepts at 0, just to make it as easy as possible. And so first of all, I want you to look at this, I'll say teal is a slope of 1, and the purple is a slope of 3. And notice that the slope of 3 is very steep. It's like it's close to 0, close to 0, close to 0, boom, explodes, comes up, now it's close to 1. While the slope of 1 is more of a gradual increase. It's not as, it doesn't have that explosion. When I have large values, the larger the value, the more that this curve is going to look like a stair step. It's going to be very, very steep. If I had 3 million for my slope, the curve would be coming really, really close to the y-axis and explode up and then go along this way. Now for the negative slopes, it's the same story, but just going downhill instead of uphill. So for -1 here, I've got the red goes down like this. For -3, I've got the same steepness as before, but it's going in the other direction. Now the impact of the intercept is that the intercept is going to shift our curve left and right along the number line. And something that is, so the inflection point moves left if we increase the intercept. So remember in college algebra when you had shift left, shift right on your functions? Well, things will go in the opposite direction as we would expect it because of where that 0 parameter is going, or the 1/2 like the 0 of z is going to be. And so here, when I have an intercept of -3, you'll notice that the curve is farthest to the right when the intercept is -3, and it's farthest to the left when the intercept is +3. So, and then we can see the shifting over between the two. So when I have +3, I'm far left, then +1, -1, -3. Now, for estimating the parameters of a logistic regression model, we're going to use maximum likelihood estimation. And by far the most common way to do this in R is with the GLM function. There are alternatives in other packages, but this is pretty standard for this. And so let's go ahead and do this. If I remember correctly, so this is like I think this is a diabetes, like a data. All right, so here I'm just giving I've got some data. I'm formatting my data, and now I'm going to say that type, which is my target variable for this one, it's got 2 different levels, depends on glue. I think it's glucose. And now for the GLM function, I specify the formula, I specify the data that the values are coming from, and I have to specify that I'm using the binomial distribution. All right, and so then we get our results. So for the slope, so here is my estimated slope of 0.04. So then here I see that's positive. It's not a very big positive value. And then I see approximately -6. So I know that's going to be like shifting to the right compared to what if I had, a more, if I had a positive value on there. So let's actually go ahead and take some values and see what it actually looks like. All right, so now here you can see that it's shift. So before, on all the curves on the baseline curve, when I plugged in 0 was when I got a probability of 1/2. So we can see that the curve is shifted to the right because of that intercept. And the slope it's really hard to see because I didn't put the baseline curve on here, but we can see that it's pretty gentle slope compared to the other ones that we're looking at. And so with a positive slope, we know that it's going to be increasing from left to right, and yeah. So that as the glue increases, the probability of type increases also. Now there are other curves that we could use. We don't have to use the logistic curve. Honestly, we could use any function that that was strictly increasing, continuous, has an asymptotic 0 limit as x goes to -infinity, asymptotic limit of 1 as x goes to +infinity. Any curve could do that. So like a lot, a lot of cumulative distribution functions would work for this. So we actually have like tons and tons of options that we could use. Now there's some ones that statisticians that have established as being like more common than others. The first one is the probit function. So the probit function is going to use the cumulative normal distribution to model the probabilities. This is by far the most common alternative to the logistic curve. All right, so here so instead of having the logistic curve that I showed you, it's going to be the cumulative normal distribution instead. And we're going to use a mean and a variance estimates to, correspondingly to tell us what the slope and the intercept are when I only have one predictor variable. And so here we can see the curve. Now, as I plot these curves, I'm going to go from a probability of 0.001 to 0.999. And so here you can just kind of see what it looks like. And you can see that goes from like -2.5 to 2.5 on this particular graph for the z value. Now, arctangent. Now here we're using the Cauchy distribution. And if you remember, the Cauchy distribution does not have an expected value. This is going to be a heavy tails distribution. So a lot of times when we need to analyze something to see from a theory point of view, if an idea holds, the Cauchy distribution is a good approach to like battle test it to see if it's actually correct. For us, we're not going to use the Cauchy very often. We're not going to use arctangent much because it usually the logistic curve does a good job. If that doesn't do good enough for some reason, probably will do it. The Cauchy link function, I've never had success with it. I've gotten wonky results that I don't trust. I don't trust the coefficients. They just seem unreasonably large, positive or negative. So I recommend you don't use this, but it's an option in our tool belt if down the road for some reason you need it. All right, so here is my cumulative function, that curve. I'm using arctangent, and we are rescaling and shifting to put it between 0 and 1. And now you'll notice that it goes really extreme on this. So when I put this range of probability values to get all the way up to this probability, all the way down to this on the curve, I had to go super far out along the number line. And so because of these features, I recommend you don't use it, but it's an option if you find yourself needing, alternatives. Now, the complementary log-log, this is almost exclusively used for survival analysis. I've never used this for the purpose of like predictive analytics, but it's a feature in the GLM function. So we can use it if we want to. We tend to use this for modeling extremely likely or extremely unlikely events. And so like in a situation where we have very lopsided probabilities on this. Now the curve is asymmetric about its inflection point. Now here is how we get our curve. Here's our probability, like this. And you can see this is why it's called log-log. And the probability is the inverse of this function. And you'll notice that this is an asymmetric curve. The ones that we looked at previously, they were symmetric about their inflection points. All right, so for your homework, go out, just fit some logistic regression models. So what I want you to do, I want you to use 3 different continuous predictor variables, fit 3 simple logistic regression models, and plot the 3 curves along the same baseline, along with the baseline logistic curve, and just see what they look like. So I'm going to take variable 1, variable 2, variable 3. I'm going to fit 3 simple logistic regression models, once for each predictor variable. And then I'm going to plot those, and I'm going to plot the baseline logistic curve, and then I'm going to look at them. And that's your homework assignment. All right, well, that's all I've got for you. Life is short. Do math.